Yes. So it has recording has been started. So yeah. Once again, so good morning to all of you. So today we are going to start our discussion on op-amp. Op-amp stands for operational amplifier. So OP stands for this operational and AMP stands for this amplifier. So far I think you are quite familiar with this term. What do you mean by amplifier, right? So amplifier is, and you can say, if you say like this is an amplifier, right? Then you give some signal here. Then at the output, you are expecting an amplified version of the input signal, right? Right. Now, why the term here has been used as operational? This operational, before this digital computer age, previously we will like we used to use analog computers, right? So at that time, all the operations has to be done in the analog domain, right? During that time, the basic operations like addition, subtraction, integration, differentiation, all these things were performed using this device, op-amp. So the name has come from there. That is called the operational amplifier. Okay. So I hope that that part is clear to you. Why it is called operational? Because addition, again, addition and multiplication is just, you have to repeat it couple of times, right? That way. Subtraction, integration, differentiation, all these operations, this can be performed using this op-amp. So that's why the name is operational amplifier. Right. And this operational amplifier, actually, it is not a single device. Like, we have studied both bipolar junction transistor. Also, we have studied like before that, two-terminal device like diode. And just before, like till our last class, we have also studied this another device, which is MOSFET. Right. So far we have studied these different devices and the circuits and their circuits using and the circuits using these three. Right. So this like that individual devices, operational amplifier or op-amp is not and like type of single device, but it is a combination, or it has been made by using 20 to 30 transistors. Made by 20 to 30 transistors. So the circuit diagram and all these things are a bit complicated. So we will not focus much on the how this what is the internal circuit diagram. Maybe in the next class, if the time permits, we will discuss it very briefly, like what is the internal circuit diagram of this op-amp. But for our discussion, so we'll consider this op-amp to be as an and type of say circuit symbol that we will discuss in a couple of minutes, right? And we will see it from the external, like we will try to analyze this op-amp from its external behavior. We will not see internal transistor diagrams of this op-amp. Okay. So it is made from this 20 to 30 transistors, and this op-amp is not also very new, right? Even okay, and when we say like this can be made from this 20 to 30 transistors, so these transistors can be like you can make this op-amp by using MOSFET, also by using bipolar junction transistors. So you can use either MOSFET or BJT to make this op-amp. So depending on like which technology, either MOSFET technology or BJT technology you are using, the op-amp characteristics, some of the characteristics will slightly differ. Okay. And this op-amp is not very new that way. Even in, I think in 1965, first this op-amp first introduced in 1965. Okay, and that op-amp, that name was this mu A709. Where this, even if today also, if you like try to search it, that what this mu A stands for, this mu A stands for the name of the company. Okay, this mu A stands for the Fairchild. The company name is Fairchild. Okay, Fairchild Semiconductor. 709 is the name of the op-amp. Okay, so this is the general convention. The before head, these two digits or these two letters stands for the company name, then the name of the IC. So that way, it consists of 20 to 30 transistors. 20 and 30 transistors has been packed in a single integrated circuit. So this op-amp is available in terms of this IC only. In your laboratory, rather, the most commonly used op-amp would be 741. Some people say it as IC 741. That is, it is because you understand from here that it is 20 to 30 transistors and they have been packed inside an integrated circuit. So it is IC 741. You can say it in this way. Or if it is from, suppose from this Fairchild Semiconductor, then to be more precise, you can say it as MUA 741. Right? And see this MUA 741, this has also been introduced in the 60s. Okay, this has also been introduced, like this is first was in 65, then later after that the 741 was also introduced. So that is also in after few years of this first introduction, and still today we use this 741. This op-amp is quite versatile, and now not only this Fairchild Semiconductor, means Fairchild Semiconductor that way does not exist like today. That way. Now it has been splitted into different other companies, right? So this now you can find of different names here. These two letters that would be different here, but 741 would be the same. Okay. So this is a brief type of brief description or yes.
Sir,
Hmm.
these are commercial codes for those semiconductors or what?
These are
Like MIUI 709, MIUI 741. These
uh,
are kind of some codes to
no,
describe
these are
them.
the name of the IC. Suppose if you go to a shop, suppose in an electronic shop, if you ask like I need an op amp, they will ask you like which op amp you would like to have. Right, then you have to say like 741. So if you say 741, then they will understand, okay, you are asking for 741, that is a particular IC. Then they might
Okay,
ask if they have
any
suppose different
convention for naming this?
uh-huh.
Is there any convention for naming this like why 741 or it is just arbitrary?
No, it is like this. There is a convention for this previous two, like to the total nomenclature, but I don't think it's a any convention for this like 741 or something like that. Even for diode or the you can see it's a type of different names. Okay, maybe in the next class I will try to give you a bit more light. I mean, try to fall more light on this nomenclature of this different ICs. Okay.
Okay, sir.
So okay, let me put it down here, nomenclature. Okay, I have written it. So okay, definitely in the Wednesday's class, I will try to give you more exposure on this. Okay, if there is any particular rule like for Y741, right? But generally, it is like from one generation to another generation, these names actually differ. Okay, and if some company has been designed, and then later on people will follow that name. Only thing is that the previous two digits this will change. This is for nomenclature of op-amp, but nowadays you will find like different nomenclatures as well. So now if you consider like circuit, if you have to see the circuit symbol of op-amp is like shown here. So you can see from here. So it is an triangular like a type of this shape, right? Triangle shape, where it has two inputs. In one of the input is called V in one, other one is V in two, if we are denoting it like that. Then with one input, one negative sign is, you can see the is been denoted here with negative sign, and the other input has been denoted as a positive sign. This is the output, V out, written here. Other than that, you have two supply voltages. One is this V plus supply, other one is this V negative supply. Suppose if you have plus 15 volt, and then you might have the minus 15 volt for this op amp. So remember, this is the DC supply voltage for this op amp, And this is, you can think of like if it is a B, like if the transistors inside here this BJT, then you can see this is a plus VCC and this is minus VEE, right? If it is for MOSFET, then it is plus VDD and this one is minus VSS. Right, that way you can think of. Okay, so it's then from there it is quite easy to understand that you should have always apply this V plus supply and V negative supply. Otherwise, this op amp will not work. Right. So in lab, when you are doing it in the particularly in board, many case like okay, many you know, in many circuits we generally do not even draw or write this V plus supply and V negative supply. We simply write it. You will also see that we simply denote it the symbol like only like this. Okay, and if the circuit is denoted in the if the op amp is denoted by this symbol, then in many cases students forgot to connect this V plus and V negative supply, and then they found their circuit is not working as expected. Then after inspection, it has been found that the student has forgotten to give the proper DC bias to this op amp. So remember that always you should have to always apply this supply voltages, plus supply voltage and minus supply.
Sir, then in the internal configuration, all the collectors, if it is BJT op amp, then all the collectors are connected to V plus supply. Will it be like that?
It is a bit different because there will be like multiple stages of op amp. It is not only one stage. One of the stage would be amplifier. One stage would be like controlling the resistance, input impedance, output impedance. Okay, so there are a couple of like stages are there. So it would be like maybe it we can see this in this internal diagram in the next class. Okay, quite quickly. Okay. So as of now, let us just focus only on this thing, circuit diagram, because if we introduce everything together, it will be much more complicated for you. First, try to understand this from this circuit diagram, then we will try to see a bit briefly as like what is the internal circuitry of an op amp. Right. So here, so one signal is this, connected with this negative, like is marked with negative, and the other one is marked with positive. The terminal which is marked with this negative, that is this one. Okay, this terminal is called the inverting terminal. Right, this is called inverting terminal, and the terminal which is connected with this positive, right? This is with this positive. This terminal, this is called non-inverting terminal. So suppose at this inverting terminal, okay, the name is inverting because suppose here you give an sinusoidal signal like this, right? Then at this output, you will get an amplified, but the signal would be inverted. Okay, there will be a 180-degree phase shift. So you can just still, I mean, I am this is our first. Just now we have started, so I am trying to simplify this thing quite drastically. So eventually, you will not get an output like this if you are operating it as in an open circuit. Okay, but those things will come later on. Okay, so try to understand from here. This inverting means if you are giving a signal here, the inverted shape you will get at this output. Okay, and for this non-inverting, it is the opposite way. If you are giving an sinusoidal signal like this, then at this output you are expected to get an amplified, but the signal would be in phase with this input. Right? This is in phase, and here you can see 180-degree phase shift. Right? So that's why the name is like inverting terminal, and the other one is this non-inverting terminal. V plus supply, V negative supply we have already discussed. V output is this output. So that way you can see you have two inputs, right, and one output. Other than that, you have plus supply voltage and negative supply voltage of an op amp, right? Okay. Now, let's see some of the important characteristics of ideal op-amp. So ideal op-amp can be depicted like in this way. So here you already know this is the now negative terminal, means the inverting terminal. This is the positive one. So this is the non-inverting terminal. And with this, we have connected one supply, or you can say like one signal. If like it may be DC, it may be an AC, right? It is like V in one, as shown here. And here we have connected with the non-inverting terminal and signal which is V in two, right? And between these two input terminals, you can see this inside, actually they are open. Means you can, maybe I can show it like this. So inside they are open. Means these two terminals are not connected, input terminals. And so now if you look from here, right? If you look from here, so what is the resistance, input resistance you will see from here. As this terminal is like open, then you will see that, after that there is nothing. So it is the resistance is infinite. So the input resistance is infinite. Similarly, if you look from this terminal, again here this is open. So that way, this terminal, like this out resistance of this terminal is also infinite, right? So that way we can say the input resistances, like either you look from here or you look from here, right? The input resistance is infinite, right? So if the input resistance is infinite, so that way, like if I ask you, then what is the current that is flowing through this terminal? Right? If there is no other branch, then the current which is entering to this op-amp would be zero. Definitely the current which is entering in this terminal, non-inverting terminal, that would also be zero. Right? So this is one of the important property of ideal op-amp. Okay. And in the output side, you can see in the output side, it can be considered it as the circuit like this. There is a voltage source which is like this side is plus, this side is minus, and the amplification is AOD, right? This is the amplification AOD into, and what it has been amplified, it is amplifying the difference between these two signals. So what is the difference between these two signals? Difference between these two signals is this is plus, this is minus, and this is V into, this is V in 1. So the difference is V into minus V in 1, right? So this is the difference that has been applied between these two input terminals, right? And this op-amp will amplify that particular difference, right? And so this is then the gain or differential gain of that op-amp, right? And so this differential gain of this op-amp, if it is in open loop means there is no connection between input and output, between inputs and output. See, here is no resistance or no terminal, means this is not connected with any of this terminal. Then this AOD or this open loop differential gain for this ideal op-amp is very, very high. Actually, it is very close to this infinite. So the gain of differential gain of an op-amp, of an ideal op-amp, is infinite. So this is the voltage source, right? This is a dependent voltage source. Dependent voltage source resistance, any voltage source internal resistance is zero, right? So if you look from here, right, like similarly what we have done for our analysis during our BJT and MOSFET, like what is the output resistance if you look from here? So you have to replace it with the internal resistance of the voltage source. Voltage source internal resistance is zero. So that way output resistance would be zero, right? So the output resistance of op-amp is zero. Input resistance of ideal op-amp is infinite. Differential gain is infinite. Okay. Next thing is what is the common mode gain? Common mode gain means suppose this op-amp you are operating it like this. This is minus plus. You have shorted this to terminal and you have applied one signal here. V in is here, and this is the output, right? So in that case, what is the what should be the output? Because the same signal has been applied to both the minus and plus terminal. So that way you can see the same signal if you just put it here. The V in 2 is equal to actually here now V in 1. So that way this is 0. So that way for ideal case, this output is also expected to be 0. That means the gain, right, that common mode gain is also expected to be 0. So ideal op-amp common mode gain is expected to be 0. Differential gain is infinite. Now the thing is that bandwidth, as I mentioned, like this signal may be a DC signal, this signal may be an AC signal. This op-amp works for both AC as well as DC input signals. So when you say like an AC signal, then obviously there is a term which is called frequency that will be attached. And we have also seen for this our amplifier design in BJT that due to the capacitances like internal capacitances as well as the external capacitances, coupling capacitors, right, bypass capacitors, this op-amp or this a particular amplifier also have some frequency response, means it will also have some bandwidth during which the gain means within which the gain of that particular amplifier will be constant. Right? You remember this type of characteristics we have done during the BJT analysis. This is gain versus frequency, and we have observed this type of plot. Right? So here, this is the bandwidth. This is the 3 dB point. Right? This is the 3 dB. This is the 3 dB point, and this is the bandwidth. So we have seen for this type of amplifier, the bandwidth is fixed, means limited. Right? However, if it is an ideal op-amp, this bandwidth is also expected to be infinite. Right. So remember what we are what we have discussed so far. Everything like considers for this ideal op-amp. Remember that. But in reality, there is nothing called ideal. But it would be close. We'll try to achieve this type of characteristics. But in many cases, we'll see that we will deviate from these characteristics. Is this properties are clear to you? Ideal op-amp character. Ideal
Sir,
op-amp.
please repeat bandwidth.
Bandwidth. Okay. So have you understood like what is bandwidth?
Yes, sir.
Okay. So if you have understood like this bandwidth, okay, bandwidth is, suppose you made an amplifier, then plot its gain versus frequency. Then you will find a characteristic something like this, right? Then this is the mid band, this is the, let's call the mid band characteristic. This is the lower one. This is the, here you will see that the gain will fall. This side also gain will fall, right? Then from here you have to take that 3 dB point, right? Here also you have to take, like from here you have to go below this 3 dB, right? 3 dB point. Then the separation between these two in frequency, right? This is called the bandwidth of that particular amplifier. So this is what we have seen for this BJT amplifier, a single BJT CE amplifier. BJT, better to say, like CE amplifier, we have seen this type of plot, right? So it is bandwidth is finite, right? Maybe suppose it starts from here, like eventually I have also shared with you one video that is recorded in the lab, and for that it was like up from 50 hertz. This point, I think, if I remember correctly, it was around 50 hertz to this was around, I think, 400 kilohertz or 400 or 500 kilohertz, right? So the difference between these two is the bandwidth. So the bandwidth is finite, but for ideal op-amp, it is infinite. That means you can use any frequency, means any signal of any frequency, and this op-amp is expected to give a similar gain, similar type of gain for the frequency, for any frequency that you are giving at this input. Okay.
Sir, sir, I am not able to understand this common mode gain.
Common mode gain. Okay. So have you understood this plot?
Sir, in this figure, sir, both positive and negative are connected by the same voltage source. So, sir, why there is need of writing positive and negative?
Why there is need of writing positive? To identify like which one is the inverting terminal and which one is non-inverting terminal.
Okay.
Okay. So here both signals has been applied, right, in this two terminal, right? And here then what is the expected output? Again, it would be like gain into the difference, right? Then what is the difference here? Difference is nothing, right? Basically difference is 0. right? So that way we can say that when a common signal has been applied between these two terminals, the gain of this amplifier is expected to be equal to 0. Okay.
Okay. Yes, sir.
So can you explain this open loop differential gain? I didn't understand why it is infinite.
Which one is infinite?
Open loop differential.
Open loop gain, why it is in this one? Are you referring to this?
Yes.
Okay, why it is infinite? So like it would be tough to tough to explain why it is infinite. It is actually very high. So that means inside you have some stages inside this op amp. Okay. So say this is that amplifier which is increasing the gain, and suppose that gain you have made say 10,000. So this 10,000 is very high.
Yes, sir.
You understand my point? So it is the internal design because of which this gain is expected to be very high, right? And if it is suppose very high, then we can say like for ideally, I mean ideally we are expecting it to be an infinitely very large number. But when you make practically, you will see that you cannot really make infinite, but you can really make something. You can merely make the gain which is pretty high, but not infinite.
Okay, sir.
Okay. So what about then the practical op amp? So for practical op amp, see the difference. For practical op amp, difference is like this. See, earlier between inverting and non-inverting terminal, there was the resistance was infinite, right? But here you can see we have a resistance here. This Ri, right? And this Ri is actually not infinite. So Ri is finite. So the input resistance of this op amp is now finite. So this is a deviation, right? Okay. Then here this V plus supply, V negative supply, okay. Another important deviation is this one. If you notice the previous diagram, this one. So here we do not have any resistance at this output of this op amp, right? But for practical op amp, we do have a resistance which is connected with the output of this op amp. So as a result, how does this resistance would impact? So you can clearly see earlier. Okay, let me go from here. Earlier, this is the voltage which would be available at this output terminal. So if you apply any resistance, right, whatever resistance, the entire this voltage will be dropped across RL, right? However, for practical op amp, if you connect this resistance, right, if this RL is much higher than this R naught, then only almost the entire voltage would be dropped across this output, or this output would be equal to this A naught D, means the differential gain into the difference between these two, right? Only when this RL is much higher than this R naught, right? So that means the output for this practical op amp would also be dependent on the output resistance, output external resistance. So that way the difference is here. Earlier, we have seen the output resistance of op amp was 0. But for practical op amp, the output resistance is not 0, but it is also finite. Okay. Another important difference is this AOD. I hope that you are able to understand from here. This is the input, one input. This is the another. This is another input, and the difference between two is this is plus, this is minus. It is VID, and this output is expected to be this differential gain minus the difference between these two. So the difference between two VI2 V into minus V in one, which is nothing but this VID, right? Okay. Here, earlier we have said that VOD is like infinite, but for practical op amp, it is very high, but not okay. Let us not write with infinite because you cannot define it's infinite. So it is very high means it's moderately high, but it is not infinite. AOD is not infinite. So these are the important deviations of practical op-amp. So as a result, if we plot, say, if we plot this V output versus VID. So remember what is VID? VID is the difference between these two input voltages, right? Then what we can expect when this difference is 0, then output voltage is expected to be 0, right? When the difference is plus, right? Slightly, slightly positive, the difference. Then this op-amp is expected to give an output voltage which is expected to be very high. But remember, really, can we get an infinite voltage at this output? No, because the output voltage, which is a positive voltage, that would be limited by the supply voltage, right? We know that this supply voltage, we cannot, go beyond this supply voltage. So this would be limited by this supply voltage, right? Similarly, if this VID is negative, so if this VID is negative, you can see if this VID is negative, that means V in 2 is lower than V in 1, then you are expected to get a negative voltage at this output. But this again, that negative voltage would be limited by this V negative supply voltage. So V negative supply voltage. Eventually, you will not be able to get exactly at this output at V supply voltage. But what you will get? You will get a slightly lower value than this V positive supply. Okay, that is because, just to explain it, quickly. Suppose if you were implementing it using an CE amplifier, right? And during when this is in saturation, you know that this voltage. When this is saturation, this voltage means, suppose if you are taking some output and you are taking this output, considering that you will get in between exactly the VCC, so that you will never get, right? There will be always some voltage drop in this total path somewhere, and you will always get some the output voltage which is bit lower than this VCC, or means the supply voltage, right? So depending on which technology you are using, this difference can be from 1 to 2 volt. This difference can be 1 to 2 volt from the supply voltage, or it can be as low as 20 millivolt. Right, so depending on the technology, but you will never get exactly equal to this V positive supply or V negative supply. There it will be always some bit lower than the supply voltages, plus supply voltage, negative supply voltage, and that difference will depend on the technology of op-amp, the means inside circuitry, which type of circuitry you are using, right? So, but yeah, but if it is in any question, okay, no other information is been given, and the op-amp is operating in this open loop, then you can assume that the maximum positive output voltage would be nearly equal to, or say like equal to, this V plus supply, and the maximum negative output voltage would be equal to V negative supply, right? Okay. One more important thing is that when this is positive, see, when this output is positive, right? So that means one current is flowing from this direction to this direction, right? That means op-amp is acting as a source, current source, right? It's supplying the current. However, but when this this voltage V naught is negative, then one current has to flow inside of the then only you will get the output voltage negative. Right? So then the op-amp is acting as a current sink, right? So one case it is output is acting as a current source, and the other case output is acting as a current sink. So also there is a question for practical op-amp. Then what would be the maximum value of current that op-amp can supply, and op-amp can act as a source as well as a sink. So what will be the maximum voltage? Either this direction current or this current. So that way, typically it has been considered this current maximum value is around 20 milliamps. So 20 milliamps is the current, maximum current that this op-amp can act as a, give as it, op-amp can supply to the external load, or op-amp can take this around 20 milliamps current, that is the maximum current, and from and load. One more important thing to notice, because of this AOD, which is the differential gain, open loop gain, right? AOD stands for A is the gain, is the open loop, and D stands for the differential, right? So as a result, you can see this, there is a slope between this output and input, right? And the slope is not, if this gain has been infinite, then that would be in a straight line, right? But here, as we mentioned, it is very high, but not infinite. So as a result, you will also have some, finite slope here. So that means when VID value is somewhere here, right? VID, when the value is here, the output is not even this one. The output will not saturate. See, the output would be here, right? So until and unless you are going beyond this point, right? You are going beyond this point, VID is beyond this, the output will not saturate. Same thing will also happen on this negative side. Okay. Yeah. Is this part clear to you?
Sir,
Hmm.
sir, here VO is the AC signal, right? So why are we considering the upper bound as V plus supply?
VO is the, no, it can be AC, it can be DC. You can apply here DC voltage as well.
So
Okay.
sir,
Huh.
in the op amp, we are considering every signal, I mean every transistor operating in small signal. Is it something?
Every transistor operating in a small signal, okay, that is a good question. But yeah, for that again, some more explanation is required. So, but for the time being, for today's class, you can consider it like this. You can apply here one AC signal. You can apply here some DC signal as well. Say this is plus 500. Eventually, now why you are considering this limit, that was your question. So eventually, suppose if you are applying some voltage here, say the voltage is say like say 2 volt, okay, this 0 to 2 and this is 0 to minus 2, okay. Then at this output, what you will get is not actually an sinusoidal, okay, for this open loop case, because see the gain is very high. So eventually, for a very small of VID, right, a very small difference between these two, the output would be saturated to this point. So basically, for this case, for this input, what you will get, and if you are applying this signal here, and if you are grounding this one, then what you will get an inverted square wave. Are you able to understand? Means, is it clear to you? See, this gain is very high, right? This gain is very high. So once this is positive, slightly positive, this output would be here negative, because it is you have connected it with this terminal and you have grounded this, right? So the output would immediately become negative, right? Then as you are moving up, fine, but still the output cannot go beyond this point, right? So output will be fixed to
Get
this.
how it is bounded.
Huh?
I didn't get how it is bounded by the supply voltage.
Okay, then okay, suppose you made an amplifier, okay, uh, you have made an amplifier supply voltage is plus say 12 volt, and here the signal that you are giving is say 0 to plus 2 volt, okay, and tell me and say the gain of this amplifier is say 10, then what is the expected, what is the, like, what would be the output waveform? Say this is an CE amplifier, what would be the waveform?
So inverted sign
Inverted, inverted sign, but what will be the magnitude?
20.
Huh? What would be the magnitude? Yeah, you are saying inverted sign, that is right, but what would be the magnitude of that?
So shouldn't it be 20?
12.
Should it not be
20.
20? Why? You forgot this part. I think then you have forgotten this part. You remember we have considered this type of characteristics, and from here we have used this load line and see that what is the maximum voltage, right? Here this voltage is the VCC. This is 12 volt, right? So if you are going from here, will your output not be cut here? You forgot. The output will be
Okay, sir.
limited
It
by,
will be clipped.
it will be clipped, right? So here it will be clipped, right? And here this will be clipped.
Okay.
Right, but why it is still for this part you will be getting an sinusoidal part, because here the gain is 10, right? So that's why you are getting, and still for this part, for this region you will still get that, slightly that curvy nature, right? But for this op-amp, if this gain is suppose very high, say gain is 10,000, okay, so if the gain is 10,000, so that means immediately when you cross some positive, immediately when you have this one slightly positive, the output would be immediately become to saturate to this value. But then after that you keep on moving this point, but your output will be keep on saturating at this output, right? Then when you are going to this one, it would be inverted, and again it will reach this, keep on constant, and like this. Is it clear to you now?
Yes. Yes, sir. Thank you.
Okay. Okay, so I think then now we are in a position to start our discussion. One more amplifier, which is called the inverting amplifier. So from the name itself, it is clear that this is an inverting amplifier. So the signal, or the either it is an DC signal or an AC signal, that we will be applying at this inverting terminal on, right? So this is an signal is applied at this inverting terminal, right? But another important difference compared to the previous whatever we have discussed so far, you see, this output is now connected with an resistance with this, right? So it is not anymore an open loop system, but it is a closed loop system, because this output is connected with the input, right? And eventually it is giving some negative feedback. So that those things we will see later on. Okay. So, but I think for the time being, it is important that you understand that this is not the open loop system, right? Okay. But still, we can consider that inside this you have a, and right, we are considering that op-amp is ideal, and this is AOD, this is VID, right? And still this open loop gain is infinite, is very high, right? Okay. So remember that this AOD is the open loop gain of that amplifier. It is not the closed loop gain of the amplifier. But now it is a closed loop system, and we have to find what is the closed loop gain of this particular circuit, right? So always remember that these two difference, open loop gain and closed loop gain. Open loop gain means when the output is disconnected from the any of the input, and at the time the gain, or the gain of the op-amp itself, is the open loop gain. That is always going to be a very, very high. For ideal op-amp, it is infinite. Whereas when you connect this, then the op-amp gain will drastically reduce. We'll see that reduce, and that particular gain of this total system is called the closed loop gain. So now what we will be trying to try to find is the closed loop gain of this inverting amplifier. Okay, so this is infinite, fine. So here V in is here, V in is connected through this resistance R1. This is say node 1, this is node 2. So let us say V2, this one node 2. So what is the potential at node 2? This is grounded. So V2 potential is 0. What is the potential here? Say V1. We don't know as of now. So say V1. Okay. So this is plus, this is minus, right? So what is VID? VID is the difference, plus positive minus negative. So it is basically V2 minus V1. V2 is 0. What is V1? V1 is, we don't know. So it is minus V1 only, right? So it is VID equal to minus V1, right? Okay. Now, AOD, okay. So what is the output voltage? The output voltage, say if it is like this, Then the output voltage is obviously, this is not, no other resistance is connected between these two. So whatever is the voltage that will appear across this V0. All right. So this V output would be equal to A naught D into VID. Okay, very fine. So this is equal to AOD. This is nothing. And VID is equal to minus of V1. Right. Okay. Here, this is infinite, very, very high. Right. What is the output voltage? Output voltage is always finite, right? Because just now we have seen the output voltage, maximum voltage that it can reach is this, either V plus supply or V negative supply, right? So the output voltage is always finite. So output voltage is finite, gain is infinite, right? Then what would be the value of this V1? Then V1 would also be at zero potential, isn't it? So V1 would be also now here at zero potential, because this is infinite, this is finite. So this is a finite number, by you take infinite, so this V1 also be equal to 0. So that way you see this potential here is similar to this potential, right? So basically these two nodes are actually shorted. That way you can think of, not physically shorted, right? Virtually shorted, right? And this is grounded, this is physically grounded. But this point is not physically grounded, but it is virtually grounded because the potential is 0. Why we are saying it is virtually grounded? Because see, if you give if some current is flowing, that current cannot go to the ground here, right? Because it is not connected with the ground. But the potential of this particular node is 0. Right? The voltage of this node is 0, but it is not physically connected with the ground. Means for this, suppose some current is coming, say from somewhere, if some node is physically connected with the ground, right? Say from some transistor, then the current can flow completely through this ground, right? But for this case, this potential is at 0, right? But the current cannot flow to ground here. So it is called the virtual ground. So this is the concept which is called the virtual ground. And similarly, we can also say like these 2 points are actually shorted, but not physically shorted, virtually shorted. So that way we can also say virtual short. So please remember these two things here. Basically, they are the same thing, right? If it is at ground potential, then it is ground. Basically, they are. If it is at different potential, then this would be also at the same potential, right? So this concept is important because this we will be using, again and again during our analysis of op-amp. Okay. Okay. So if you have understood this part, then let us go ahead and try to find what is the closed loop gain of this inverting amplifier. So for that, say the current which is flowing through is I1. Okay. Then what is the current which is flowing through this, going inside to this op-amp? What is the current?
0.
Sir,
Zero.
If
it is
R1.
no, the current which is going inside to this op-amp, it is 0, right? Because its input resistance is infinite for ideal op-amp. So this current is 0. So that means this I1 current, it cannot go to here. So I1 should have to flow through this only, right? And it will come here, right? Okay. So that way, if you want to find what is this I1, then I1 would be equal to V in this node minus the potential of this node, which is 0, we have found, by R1. So this is equal to V in by R1, right? This current. Okay. Now, if you try to find, then what will be the V output from here? So V output,
I1 R2.
I1 R2.
R2.
Should it not be a minus sign there? Because current is flowing through like this. So this would be plus, this would be minus, this is grounded. So this V output
Yes.
would not be a minus, there will be a minus sign, right?
Yes.
Okay.
Yeah.
So here it is I1. The value of I1 is V1 by V in by R1, right? This value that we have already found. This is R2, right? So there will be a minus sign here. This minus sign we have to do. So it is R2 by R1 into V in. So here V output by V input, because if you are to find the gain, that would be equal to R2 by R1. So you see, this is the closed loop gain. So you see the closed loop gain of this particular inverting amplifier is given by this R2 by R1 only, right? And see, in this gain, the expression of this gain does not contain any parameter of this op amp. So it is completely dependent on the external resistances, right?
So can you re-explain why that all the current flows through R2 only, not through the op amp?
Okay, that is because let me draw it then again. This is V in, and then you have this R2. Inside you have an op amp. Now the question is, can the current go inside to this op amp? No, right? Because the impedance here, it is open, right? So no current can flow through this. Then whatever is the current, that entire current has to flow through this path only. There is only one path, na? It cannot go inside.
So,
Is it
we are
clear?
considering an ideal op amp.
Yes, we are considering it an ideal op amp.
Okay, sir.
Okay. Okay. Right? Okay. Now, for this case, if we want to look from here and try to find what is the input resistance from here, right? Then it is quite easy, right? Input resistance, how we will find? To find input resistance, again, you can right? It is R2, it is R1. This is 0. So the potential here is also 0, right? You apply one known voltage, so it is V, right? And you try to find the current, right? So here you know this V would be equal to this I into R, right? And what is this R? R is basically the input resistance of this, right? So that way R in would be equal to V by I, right? And okay, what is this V by I? Okay, again from this, it is not even to do the analysis here, because from here it is quite easy to understand. See, if you look from here, what is the input resistance? This is grounded, right? And this is grounded, means virtually ground. And here there is only one resistance. So if you look from here, so obviously the resistance, input resistance would be equal to R1 only.
Sir?
Huh.
Sir, can you please show in the circuit where is R in located?
Where is R in located? No, R in is not that way located. R in we are considering, suppose if you have to see from here, okay, and to find what is the input resistance, okay, if you look from here, okay, you do not know what is inside, okay, if you just look from here, what is the resistance, okay, of this block, this total amplifier, okay, then that input resistance is coming out to be R1 only. So R1 we have not connected, we are just trying to find it out, what is the input resistance of this amplifier. Okay.
Okay, sir.
Okay, I think we have to stop here because your time for the next class is also approaching, and I don't think I will be able to finish this next discussion within 2-3 minutes. Okay, so next would be like this inverting amplifier having a finite AOD. So here we'll try to introduce one more non-ideality factor. But we still will assume that the input resistance is infinite. This input resistance is infinite, but what we'll assume that AOD, that is a differential gain, that is not infinite, but that is finite. And from there, we'll try to see what is the effect of the magnitude of this AOD on the closed loop gain. Okay, because we have seen from here that the closed loop gain is equal to minus R2 by R1 for ideal op amp, right? So, but if it is a practical op amp where AOD is finite, then we have to see what is the gain, closed loop gain. And for what value of AOD, the closed loop gain that we will find from here will be close to the ideal case, the gain which we have found from here for this ideal case. Okay, so we'll try to correlate that in the next class. Okay, and after that, we'll also see that what is the inverting amplifier, the same type of amplifier, but instead and using a single resistance of R2, we will try to use this type of T network there. Because there is an issue that maybe I can discuss it in 1 minute in the previous circuit. The issue is here, say that we have to get a gain, where we have to make a gain of, say, we need a gain of 100, or say minus 100. Obviously, it is in inverting amplifier, so gain would be minus. So minus 100. Okay, and the value of R1 and say around 50 kilo ohm, right? 50 kilo ohm, right? Then what would be the value of R2? Then from this you can easily find this gain is basically R2 by R1. So R1 is 50, so R2 would be equal to then 50 kilo ohm into 100, right? So that way the value would be how much? 5,000 kilo ohm. So it is basically 5 mega ohm, right? Which is pretty high, right? So to get a higher gain for this type of configuration, you really have to have and use very high resistance. But this type of high resistance, we have already discussed, is difficult to get. So we will try to see, instead if we break this R2 in this fashion, in this T network fashion, then we will see we don't have to go for that high value of R2, but rather we can use some smaller values of resistance and achieve the similar type of gain. Okay, so these things we will discuss in the next class. Okay, then thank you very much. Thank you.
So Aditya, now
Thank you, sir.
Thank you, sir.